Hi everyone, and welcome to the video session for Lab 2. As you all know, I am unable to make it to class this week and next week. As such, so that we don't miss any of the classes and we don't lose any time in terms of progress of the course, I made this video so that you all can follow along at your own paces, and I hope that you all attempt to do Lab 2 at home on your own. After last week's lab, I assume that everyone has the Quartus II environment running on their laptops, and most of you have the Altera DE0 FPGA development boards that you can try the practical part of this lab. Please note that if you don't have the boards, it's not necessary and you can still follow along. Before I begin, just want to give a quick disclaimer. Any comments or questions that you have on this video, you can ask them in the comments section of this video. And if you are experiencing any errors after you've tried to debug those errors, if you're still getting any problems, feel free to take screenshots and email them to me. All right, so let's begin. Today, we're going to be looking at writing VHDL code for sequential circuits. In particular, we're going to look at the examples of the D latch and the D flip-flop, and we're going to look at binary counters, BCD counters, and modulo M counters. Additionally, we are also going to look at creating a frequency divider circuit. Now, the first set of circuits, that's the latches and flip-flops and the counters, these were covered during our review lectures, that's lectures 2, 3, and 4 on the course Moodle page. However, we haven't yet covered frequency dividers in class. So I'll not spend a lot of time on the theory behind latches, flip-flops, and counters. However, I may need to explain frequency dividers a bit. Please note that all of these circuits are very important for your design project. So today, we're going to be looking at writing code specifically for sequential circuits. And 2 weeks ago, during lecture 9, again the slides for those lectures are on the course Moodle. During lecture 9, we talked about sequential logic and exactly what sequential logic was. We also looked at comparing sequential logic to combinational logic, and we stated the main difference between sequential and combinational logic as sequential logic being logic whose output depends not only on the present value of its inputs, but also on some input history. The second distinguishing feature of sequential logic is that sequential logic typically requires a clock signal to operate. The most important thing to note about sequential logic is the concept of state or memory, whereas in combinational logic, the output changes directly as the present inputs change. All right. We also covered in lecture 9, we also covered in lecture 9 that sequential circuits in VHDL are written using sequential code. And in order for us to write sequential code in VHDL, we must use a process block. Now, the lab script here that I have, that's also on the course Moodle page, outlines all of the characteristics of sequential VHDL code and process blocks and all of that stuff here. And this is essentially a summary of what was done during lecture 9, 2 weeks ago. So I'll not go too much in depth into this. What I do want to just quickly review, however, is the general structure of a process. Remember, we write our process blocks inside of the entities of our VHDL, inside of the architectures of our VHDL project constructs. And we know that a typical VHDL construct must always consist of at least an entity and an architecture. In figure 1 here that you're seeing on the screen right now, the architecture is a behavioral architecture corresponding to some entity called entity name. Note that this is just a general template, and we'll be following this structure whenever we're writing process blocks. So the process block is typically contained between the begin and end keywords of my architecture block. Each process block has a begin and end process keyword, and all code contained between the begin and end keywords of the process is the code that executes sequentially. Making reference to the example here, the code contained between begin and end process is, in this case, the comments process line 1, process line 2, and process line 3. If these were actual lines of VHDL code, then line 1 would be executed first, followed by line 2, and finally followed by line 3. Note that for combinational logic, when we're dealing with concurrent code, the code does not execute sequentially or in order, one line after the other, but rather the lines can be executed in parallel depending on if the inputs affect some change in those lines. Whenever we're defining a process, we need to ensure that we use the process keyword to denote that we are writing a process block. If I wish, I can give my process a name. However, please note that this is an optional step and is not necessary. If I do, however, name my process, I typically would like to restate that name on the end process line. If I only have one process in my VHDL code, it's not necessary to name it. I typically use process names to differentiate or distinguish among different processes in my code. Please note that processes run concurrently to each other. That is, if I have two or more processes in an architecture, then those processes run concurrent or in parallel with one another. Only the lines inside of the process block run sequentially. The last thing I want to pay attention to is the signals that are stated in brackets after the process keyword. We stated in lecture 9 that this is the sensitivity list of the process. The sensitivity list of a process typically contains the signals that awaken or trigger the process to be executed. In other words, the process is sensitive to changes in these signals. In this case here, I have signals that I declared above in the architecture declaration section. These are A, B, C, and D of type std_logic. Within the process sensitivity list, I can also have ports that are defined in my entity. Any change in any of these signals or ports that are contained in the process will cause the process to execute from line 1 to the last line, line by line. If my process contains a sensitivity list, please note that your process cannot contain wait statements. Conversely, if your process contains wait statements, it must not be written with a sensitivity list. That being said, let's now move to Quartus and let's create our project in Quartus and type some initial code. So moving on to the Quartus environment now. And I know that thus far we've only had 2 labs and 2 practical sessions. So I'm quickly just gonna go over the steps involved in creating a new project in Quartus. And please note that you can pause the video at any time and move at your own pace. Okay, so for me to start a new project in Quartus, I can either click on the New Project Wizard button on the Quartus II start page, or from the menu bar, I can select File, New Project Wizard. Either of these options opens the New Project Wizard for me. In step 1 of the Project Wizard, the first thing I need to do is specify the folder or the working directory for the project. Typically, I can do this by clicking on the Browse button on the right-hand side of the first text box, which will take me to the Altera folder in which Quartus II is installed. From this dialog window, I can create a new folder, and let's say I'm naming this folder Lab2. Right? I click on Select Folder, and you'd see that the folder has now been specified as the working directory for the project. The next thing I want to do is give my project a name. To keep things simple, I can also name it Lab2. Please note that your project name cannot start with a number. It must start with a letter. Thereafter, you are free to name your project whatever you want. Now, while I was typing the name of the project, you may have noticed that the name of the top-level design entity was automatically typed in. This implies that by default, Quartus II sets the name of my top-level design entity to the same name as the project that I am creating. However, if you wish to give your project, or rather your top-level design entity, another name, you can specify that name in this text box here. Because I'm dealing with sequential logic and the first entity that I would like to create is the D latch, I can just give this entity the name D underscore latch. Let's pay attention to the little disclaimer above the third text box there. It says that this name is case sensitive and must exactly match the entity name in the design file. This statement relates to when I'm writing code in my VHDL design file, that the entity name must match exactly the entity name that I specify in the design file, and it is case sensitive. In other words, if I use capital D or a capital L, it must match that when I'm typing the name of the entity in my VHDL file. The last thing I want to note before we go on to the next step is that I named this entity D underscore latch. I'll explain why I gave it this name as opposed to naming it D-Latch a little later on in the lab. However, so that we don't run into any errors, let's just give this entity the name D underscore latch. After you've done all this, you can click on the next button. And this takes us to step 2 of the new project wizard, which essentially allows you to add any pre-existing VHDL files to your project. Because we're writing these files from scratch and we have no existing sequential files right now, we can skip this step by clicking Next. The third step allows me to set up the FPGA device for which I'll be writing code. Remember, all VHDL code that you write is essentially description of some circuit that you're going to be programming onto a VHDL design platform. We are working with the Altera DE0 board for this course. As such, let's configure this board. Let's configure the project to work with this board. The first thing I want to do is select the device family. For the Altera DE0 board, from the down drop here, I'm going to select Cyclone 3. You'll notice that there are a number of FPGA devices in this large list here. And to make life easy, instead of scrolling through and searching for the device that corresponds to the Altera DE0, I can use this text box on the right hand side here that's called the name filter, and I can just type in the model number of the Altera DE0 board, which in my case is EP3C16F484. And you'd notice that the filter has narrowed down my choices to 4 potential boards. The one I'd like to select is the first one, F484C6. All of the Altera DE0 boards that we are using correspond to this device name. Once you've highlighted this device here by clicking once, you can click Next to move on to the next step. Step 4 of the project wizard allows me to set the simulation tool that I'm using when I'm dealing with my test benches. Because we're going to be working with test benches today, we want to ensure that the simulation tool is installed and correctly selected. Remember that the simulation tool that we are using is ModelSim Altera and not ModelSim. Please ensure that ModelSim Altera is selected and that the format here is selected as VHDL, since we will be writing our test bench files using VHDL coding. These settings should be set by default. If your current new project wizard window looks like this, you don't need to interfere with anything here, and we can move on to the final step, which is essentially the summary page, which just recaps everything that I set before. You can go through the different characteristics of your project here to ensure that your project has been configured correctly. That is, please ensure that the project directory is set up as the folder that you created. Ensure that the project name is correct. Ensure that the top-level design entity is your desired design entity name. Ensure that the family name is selected as Cyclone 3 and that your device number is EP3C16F484C6. Now, all of these steps were covered in Lab 1. So, if you wish to have this stuff documented, you can always look over the Lab 1 script, also on the course Moodle page. Once your summary page looks something similar to this, you can click Finish and your new project has been created. Your workspace in the Quartus II environment should now look something like this. To ensure that everything has been set up correctly, please ensure in the Project Navigator area of the top left-hand window, that's what my mouse is hovering over right now, ensure that the device is set to Cyclone 3 together with the device number, and ensure that your top-level design entity here is set to D_latch. Currently, we have no VHDL files added to our VHDL project. To verify this, you can click on the Files tab under the Project Navigator pane here, and you notice that the Files folder of the project tree is currently empty. This means that we need to add a new file to our project. To add a new VHDL file to your project, you can simply do this by clicking on the New File icon on the top left-hand corner of the Quartus II taskbar, like this, which will bring up the New File dialog window. Alternatively, from the menu bar, you can select File, New. Either of those options will bring up the New File dialog window. From this window, we want to ensure that we select VHDL file, that's under the Design Files drop-down here. Select VHDL file and click OK. At this point, you'll have a blank text editor window in your project. Before we start writing code for the entity and the architecture, we can get the basic stuff out of the way and just type in the name of the libraries that we are going to be using for this particular VHDL file. Again, this is nothing new to us since we've covered this in Labs 1 and the last practical session that we had. We've also been covering this stuff quite a lot during the lectures. Remember, the first thing that I need to do is specify that the library that I'm using is the IEEE library. Then I want to specify that I am using the IEEE std_logic_1164 package and that I'm using all of the components for that package. To ensure that you have typed everything correctly here, please note that all of these words must be highlighted in either red or blue. If a word is highlighted in black, it probably means that you've spelled something wrong. Please verify this. Also, pay attention that at the end of every line, I have semicolons. After you've typed in the library and use statements, you can save your file and add it to your VHDL project. We do this by clicking on the Save icon from the taskbar. It looks like a little purple floppy disk to the top of the Quartus II environment here. After clicking Save, the Save As dialog window will pop up. You'll notice that the Save As dialog window is already in the folder that you created for your project, which is, in my case, the Lab 2 folder. Ensure that you have navigated correctly to this folder and that you give your file the same name as your entity. Remember, when we were setting up the project, we specified that the top-level design entity was named D_latch. Quartus II actually sets this by default for us. If this is not set, please type in the name that matches the top-level design entity from your Project Navigator section of your window. Also ensure that the file type is set to VHDL files and that the checkbox below that says Add File to Current Project is checked. From this point onward, you can click Save, and you'll notice that the name of the file has changed to d_latch.vhd, and from the Project Navigator pane of the window, if I click on the Files tab, you'll notice that the file now exists in the project. Before we type code for the D-latch, let's quickly switch back to the lab script and look at a little review of what the D-latch and D flip-flop are. Alright, now the schematic symbol for my D-latch looks something like this. And from this we can see that there are two inputs and one output. Please note that right now we are coding very simple versions of the D-latch and the D flip-flop. That is, we are coding 1-bit D-latches and 1-bit D flip-flops, just so we can familiarize ourselves with sequential coding. Now, the D latch and the D flip-flop are the sequential building blocks of most memory devices as we know it today. They are the basis of all computer and digital memory that we use, be it RAM or ROM in our computers or cell phones or tablets, etc. The D latch and the D flip-flop are somewhat similar in operation with one fundamental difference. This difference can be reflected in the truth table and the timing diagram of each of these circuits. Now, I'm not going to spend too much time on this since this was covered during the review lecture sessions. That's lectures 2, 3, and 4 done around the first couple weeks of last semester. You can always review those slides for any clarity on the topic here. Now, the main thing to note is looking at the truth table. The D latch is a level triggered circuit which, as long as my clock is a level 1, the input D, in this case 0, is translated to my output Q. You'll notice that there's a 0 there as well. Likewise, when the clock is high and my input D is equal to 1, my output Q is also equal to 1. This transition occurs as long as my clock is at a logic level 1. When the clock is at a logic level 0, however, please note that the output Q always retains its previous value. This is denoted mathematically in the truth table here by saying that when the clock is equal to 0, the current value of Q, given by Qt plus 1, is equal to its previous value given by Q of t. Let's not try to focus too much on the math, as we can also deduce this from the timing diagram. So you'll notice that in the initial stages, while my clock is at a logic level low, the input D changes from low to high. However, this change is not reflected in Q until my clock goes to logic level 1. So you'll notice that Q only changes from low to high when my clock goes high. Alternatively, for the duration of the period when my clock is low, we see here that D changes from a logic level 1 to a logic level 0. However, you'll notice that the value of Q does not change despite the fact that D changes from logic level 1 to logic level 0. And this is because we stated that when the clock is low, Q retains its previous value. Its previous value was 1. Now, we know that D changed at this point here. However, the value of D does not get translated to Q unless the clock is high. So you'll notice that only when the clock was on a logic level 1, that is here, only then did the value of Q change from 1 to 0. Now, let's apply this to the rest of the circuit. When my clock is at logic level 0, D experiences a change from low to high. However, Q retains its previous value. Now let's look at what happens during the period T3. That's this period here. When the clock is high or at logic level 1, the input signal D experiences a change from 1 to 0. This change in the signal occurs while the clock is high. Therefore, the value of D is also translated to the output Q. So you'll notice that Q changes instantaneously with D while my clock is high. Note, however, that during period T3, when the clock is low, the signal D sees a little blip here, which is not registered on the output Q because my clock is at logic level 0. Please excuse any of the background noises that you may hear. I live a little close to the highway, so if you hear ambulances and trucks and all that, you can just ignore that. All right. So just continuing along with the circuit here, again, when the clock is high, we see that D experiences a change from logic level 0 to logic level 1, and Q also sees that instantaneous change. All right. The reason why we refer to the D latch as a level triggered circuit is that as long as the level of my clock is a logic level 1, the value of D is translated to the output Q. We refer to the D latch as an asynchronous sequential circuit. And the reason it's asynchronous is you'll notice that the signal D changes quite haphazardly. Likewise, the output signal Q also changes somewhat haphazardly. In other words, it's not very synchronized, as denoted by the little blip in the output here, as well as the change in the output here. All right? To counteract this asynchronous effect, the D flip-flop affords us with a synchronized output equivalent of the D latch. Let's see how this occurs now. Now, we refer to the D flip-flop as an edge-triggered circuit. In this case, if I'm looking at the truth table, we note that the changes in Q occur when the clock is only at a rising edge. As such, this is a rising edge-triggered D flip-flop. On a rising edge of my clock, when D is equal to 0, Q is equal to 0. Likewise, on a rising edge of my clock, when D is equal to 1, Q is equal to 1. For all other values of my clock, in other words, whether the clock is at logic level 0 or at logic level 1, despite the value of my inputs D, so you see the hyphens here imply don't care values, no matter what the value of D is, when my clock is not on a rising edge, the value of Q retains. The value of Q remains the same as before. In other words, the output Q retains its previous value. Let's make some sense of this from the timing diagram now. Please note that in the timing diagram, we are only paying attention to the rising edges of the clock. That's here, 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 and here. For all other points in the clock signals, we do not care about what the value of D is. We are only monitoring the value of D at the rising edge of the clock. At the rising edge of period T1, D is a logic level 1. As such, Q goes from 0 to 1. For the rest of the duration of that period, we see that D changes, in this area here. The change in D is not registered to Q until the rising edge of the period T2. Likewise, the change in D here is not registered until the rising edge here, and all of these changes in D at this point in the timeline are not registered in Q because it's not at a rising edge. The value of D is only translated to Q at the rising edge, which means that despite the fact that this input symbol here is quite haphazard and changes somewhat randomly, you notice that the output Q is quite smooth and synchronized. In other words, low, high for one period, low for one period, high for one period, and low for one period. And this is irregardless of the haphazard changes in D. Please note also that the input signal D here is the same as we had for the D latch. I do hope that you note the differences between the asynchronous and synchronous implementations. We achieve synchronicity by translating the input to the output only on the rising edges of our clock. I also do hope that you understand the difference between a level triggered circuit and an edge triggered circuit. So now that we've done that quick review on these basic memory building blocks, we can go on to the coding of the D-latch circuit. All right, so I'm going to switch back to Quartus now. And if we remember what the schematic symbol looked like, we had simply one input and one output. Now remember, I'm dealing with a simple 1-bit flip-flop, so I'm only looking at 2 inputs of type std_logic and 1 output of type std_logic. The reason that I know that I'm coding a 1-bit std logic value is that my input signal is simply a waveform that oscillates between 0 and 1. Likewise with my clock, the input is just in terms of zeros and ones. All right, so let's quickly write the entity block of this VHDL construct for the D-latch. I specify my keyword entity. I give my entity the name D_latch, ensuring that I have the capital D and the capital L because this is what I specified my top-level design entity to be when I was creating the project. So I say entity D_latch is, and I specify my ports with the port keyword, port open brackets, D, which is for my data input, and the clock signal, colon, in of type std_logic. Specify my semicolon, and I'm going to write the code to specify the output Q. It is an output, a 1-bit output of type std_logic. Remember, your last port does not have the semicolon after it. We have the close brackets and then the semicolon. All right. After I specify the ports of my entity, I just have end, entity, and I restate the name that I gave the entity above. Again, please ensure that the name here matches the name here. A quick little useful tip is you may notice that while I am typing, a feature in the Quartus II environment called IntelliSense kind of senses the word that it expects you to type and provides you with a number of options. As long as something like this pops up on the screen, you can hit the Tab key on your keyboard and it will type out the rest of the word for you, which will make your life a little easier. Alright, likewise for D-latch, I'm just going to hit the Tab keyword, the Tab key on my keyboard, sorry, and I can just type out the rest of the line there. Okay? Alright, now that my entity has been created, I am going to write the code for the corresponding architecture. To do this, I use the architecture keyword, and I want you to note that I am now writing a behavioral architecture. In other words, I'm using the behavioral modeling style. Now, when we started VHDL, we covered the 3 different modeling styles for VHDL architectures, and these were the data flow model, the behavioral model, and the structural model. Typically, when I am writing sequential code, I am describing the behavior of the circuit, and as such, I'll be using the behavioral style of modeling. It is not the data flow style of modeling because I am not dealing with how data flows through the circuit in terms of logic gates. In other words, I'm not going to the level of AND and OR gates. All right? So by describing the behavior of the circuit, we are now typing code on a more abstract level. And the purpose of VHDL is, despite the fact that I'm typing the code in this abstract nature, the synthesis step when I'm compiling my code will synthesize the appropriate circuit on the FPGA device for me. All right, so because I am typing behavioral code, I can specify the architecture to be behavioral just because this is an industry standard, and I'm writing the architecture for the entity that I created previously. So I'm going to say architecture behavioral of D_latch is, and I can have my begin and end behavioral keywords here, and everything that I'm typing in between can go between those begin and end keywords there. All right. Now remember, I am writing code for this sequential circuit, which means that in our minds immediately we should think I'm going to write a process block. Okay. So I specify my keyword process, and I now need to determine the signals that are going to be inside of my sensitivity list. So to do this, let's quickly go back to this timing diagram of the latch. Well, what signal or port is this overall process going to be sensitive to? Well, I know that my output Q changes when the clock is high. All right? So that means that a change in the clock going from logic level 0 to logic level 1 is going to be in my sensitivity list, because a change in the clock signal will wake up my process. So I can place my clock signal from the ports on the entity above inside of that process keyword there, well, inside of the sensitivity list. Okay? Now, by placing clock in the sensitivity list there, that implies that any change in clock is going to reawaken the process. All right? Which means that when clock goes from 1 back down to 0, then the process is going to be reawakened. And we are going to account for that inside of the process. The next thing that we want to look at is for the duration of time while my clock is high, say in T3 and T4 here, I know that a change in D for the duration of time while the clock is high also needs to reawaken this process, because while the clock is high, the process is going to be reawakened at this point here because clock is in my sensitivity list. So if the process is reawakened here, then from the time I reach this point here now, the process would have already finished. And the change in D here would not be translated to the output Q at this point here. And this means that D needs to be in the sensitivity list as well. All right? So I'm going to specify clock, comma, D to be inside of my process sensitivity list. All right? Remember, your process has begin and end keywords. All right? If you did give your process a name here, please specify the name of the process in this area here after the end process keyword. Okay. Now, inside of this circuit here, I know that if the clock is at a logic level 1, then my output is going to be translated to my input is going to be translated to my output. So if the clock is equal to 1, Q is equal to D, or rather D is assigned to Q. When we looked at sequential statements in lecture 9, we looked at some of the conditional statements that are available to us for sequential code. And we specified that we can have if then else statements in a process block. Note that if statements cannot exist outside of a process block. So what this means is that I can have some if statement here saying that if clock is equal to 1, then Q is going to be assigned the value of D. All right? And let's break this statement down a little bit here. Whenever you're writing an if statement, the condition that you are testing must be stated in brackets between the if and then keywords. Clock is of type std_logic. Therefore, if I'm checking to see if it's equal to 1, the 1 must be stated in single quotations for a single bit value. The expression inside of the if statement is a Boolean expression, and it checks to see whether clock is equal to 1 is true or false. If the statement inside of here is true, only then will I execute this statement here. Remember, as long as I have that if statement, I must have an end if to end off the if block. All right? Now, you may be asking, well, why don't I have an else statement to specify the behavior of the circuit when the clock is equal to 0? And the reason I don't have that else statement is that I only want to assign or change the value of Q when clock is high. For all other values of clock, in other words, when clock is equal to 0, I don't want any change in Q because that's the purpose of the memory or state characteristics of the latch. I'm going to latch on to the previous value of Q. All right? Therefore, I don't need to have an else statement because for all other conditions, when clock is not equal to 1, Q is just not going to experience a change. In other words, Q is going to retain its previous value. And that takes care of writing the code for this D latch here. I can save the code by clicking on the floppy disk at the top, and I can compile this to ensure that everything was typed correctly. Now, this is the point where you can pause the video and ensure that all of your code is the same as I have here, and you can go through the compilation steps, and if you do get any errors that you can't figure out, again, please feel free to send me screenshots of the errors, and you can just email me those errors there. All right. If you want a quick way to get a screenshot, for example, let me just simulate some errors here and compile the circuit. What you can do is when you run into the errors, remember our output window at the bottom here will have some errors stated in red here. What you can do is use the snipping tool of Windows and just take a snip of the error and send me a snip of the image there. All right. Okay. Now I'm gonna just correct these errors here, and let's just go through some quick error correction things here. The first error I have here tells me that on line 16 near Q, it's expecting the statement then. All right. The error takes me to the line following that which I expect the keyword then. Okay, so I just look around to see if I have any floating if statements without a then statement. All right, and this one here tells me that I'm missing a semicolon because I removed the semicolon after end the process. So I can save and compile the project. For those of you who don't remember, there are 3 ways that I can compile this VHDL code. I can do so by clicking on the plain purple play button at the taskbar of the Quartus environment. I can double-click on Compile Design in the Tasks window to the left-hand side, or I can select Processing from my menu bar and click Start Compilation. All right, so let me compile this code now and see what happens here. Now, as long as you see the process bar looking at as some percentage here in the Tasks window, you'll know that the code was typed, correctly. All right. If you don't get to this process bar, then probably you have a syntax error somewhere in there. Okay. All right. Now, as long as this progress bar reaches 100% and you see all of these green ticks in the left-hand side there, you'd know that your code was typed correctly. All right. So just quickly switching back to the script now, let's see what's the next thing on the agenda for this lecture. Okay. Let me just quickly read from the script here to clarify what I was stating about the sensitivity list. All right. So we say that note that the sensitivity list contains the clock signal and the input signal, that's D. That is, the process is dependent on changes in both signals. And again, the reason for this is that the clock signal changes as expected, and whenever its value changes, the process is evaluated and the if condition is checked. All right. Now let's take a look at that line there now. Remember, we said that when the clock goes from low to high, the process is going to be awakened. Likewise, when the clock goes from high to low, the process is going to be awakened. And when the process is awakened from high to low, I have this if statement so that when the clock is low, it does not affect my circuit in any way. So if the process is awakened when the clock goes from high to low, it's going to check that if statement there, and it will see that the clock is not equal to 1 and the circuit is not going to do anything, and the process is just going to go back into its dormant stage until it is reawakened by a change in one of those signals, D or clock again. All right. Continuing the reading now, the data signal D needs to be in the sensitivity list since changes in D while the clock signal is high must be evaluated. All right. In other words, if the value of D changes while the clock is high, the process is evaluated and the value of D is assigned to Q. If D is not in the sensitivity list, then a change in D during a high clock signal will not be registered, since the process will not be reevaluated while the clock signal is high. That's a very important thing to understand there. Okay. Also note that the if statement checks the level of the clock signal. All right. Now, when I was creating the project, I asked you all to place an underscore between the words D and latch. And the reason for this is that if we had specified the entity to be something like D latch, what happens is that Quartus II actually has a D latch built into it. All right. And these in the Quartus II environment are referred to as low-level primitives. All right, and these are just pre-programmed low-level memory blocks and sequential circuits that exist for us to make design a little easier. For example, if you didn't want to code your own D-latch, you could have just selected one of the built-in low-level primitives. However, notice that these primitives do not exactly match what we are coding right now, because we are coding a very simplified version of the D-latch. Okay, so if you did give your project the name D-latch that looks exactly like this without any underscores or anything like that, you're going to run into a compilation problem. It may say something like the D-latch entity does not exist. You may be a little confused, and the only reason for that is that the entity that you have just written may be clashing with one of the low-level primitives, which is, as stated, a small architectural building block to assist in your design. All right. Okay, so now we can move on to the code for the D flip-flop. All right, and the if statement for the D latch here, that's this statement here, it takes into account the level of the clock. In other words, we're checking to see if clock is equal to 1. We're not specifically looking at a rising edge. So to write the code for the D flip-flop, we need to write an if statement that's going to look for rising edges of the clock. All right. So what we want to do now is we want to create a new design file, a new VHDL design file for our D flip-flop. All right. So again, to add a new file to your project, you're going to click on the new file icon on the top left hand corner here, or select file new from the menu bar. And the window that pops up, the new file window, I'm going to select VHDL file again, and I'm going to click OK. All right. Now remember, the D flip-flop is the same schematic as the D latch. In other words, for the simple version of the D flip-flop, I have two 1-bit inputs and one 1-bit output. So that means that I can quickly start writing the code here one time. So I'm going to just specify my library keyword again to specify that in this VHDL file, I'm going to be using the IEEE library once more. I'm going to list the package that I'm using here. Remember, it's IEEE, not IEE. If you do type the wrong thing, you'll notice that the keyword is not highlighted, and the keyword is black. All right. So I'm using IEEE.std_logic.1164 here. And again, to simplify life a little bit, you'll see that IntelliSense has brought up the down drop of potential keywords, and I can use the up and down arrow keys on my keyboard, highlight the option that I want. In this case, it's std_logic_1164, and I can just press the tab key on my keyboard and avoid having to type out all that stuff there. All right, just remember your semicolons at the end of the lines. Okay, now the entity is going to be called D_flip-flop, and again I'm putting that underscore because I don't want to clash with any of those low-level primitives in Quartus II. All right, so I'm going to give this entity the name D_flip-flop, and I'm going to specify the ports. And remember, the ports are basically the exact same thing as the D latch. All right, there are two 1-bit inputs of type std_logic. That's my D input and my clock input, and there's that 1-bit output Q again of type std_logic. All right, put my close brackets and my semicolons. And another thing is, you might see that when you hit an enter key there after typing something like that, you'd end up on with the cursor a little ways inward from the margin there. If you want to go back to the margin to make your code a little neater, we can press the home key on our keyboard, or we can just backspace those spaces there, and we can have our end entity keywords on the margin, which makes the code a little more readable. All right. Once you've written the architecture, once you've written the entity, sorry, we're gonna write the behavioral architecture of the entity. Now notice that the architecture here, behavioral, it's the same as before. I can name the architectures in different files the same thing. What I need to ensure is that I don't name the two entities the same thing. So each entity must have a unique name, and the architectures could be named the same among different entities. All right. Okay, so I'm writing the architecture for the entity that I just created, which is D underscore flip-flop, my is keyword, my begin and end keywords. So I'm going to end behavioral semicolon. All right. And again, inside of here, I'm going to be typing the process keyword now. And just as before, right, now what we're going to be doing is we have the rising edge flip-flop, and we can also write an code for an edge triggered flip-flop that is a falling edge flip-flop. So the code I have on the left hand side there corresponds to the rising edge flip-flop, and the code I have on the right corresponds to a falling edge flip-flop. All right. So I specify my process keyword, and I'm going to write my sensitivity list here now. Now notice that the sensitivity list of the D flip-flop only contains the clock signal, because the only time I want to awaken this process is on the rising edge of a clock. It will be awakened on the falling edge as well, but my if statement is going to account for if it's awakened on a falling edge. Because remember, a change in the clock signal is going to awaken the process. Okay? I do not specify D in the sensitivity list of the process because a change in D will reawaken the process, and well, the if statement will still account for that because it wouldn't be at a rising edge anyway. So you may actually see some resources, especially the past papers from Greenwich, that contain the D signal inside the flip-flop there. Personally, because I only want to check the process on every rising edge, I omit the input data signal there. All right. I'm going to specify my begin and end keywords of my process, and I'm going to have my if statement now. Now, the if statement needs to check if I am currently at the rising edge of a clock. And there are two possible ways to do this in VHDL. All right. I can say if clock, i.e. my clock signal that I defined in the ports of my entity, if clock dash event equal 1, sorry, if clock dash event and clock equal 1. All right. Now this is a special way to write the rising edge of a clock or any signal. All right. The clock dash event statement here, this VHDL statement, checks specifically edges, and this can refer to either a rising edge or a falling edge, because the event implies that there's a transition, and a transition could be from low to high or from high to low. So clock dash event checks for a transition, and it says if I'm at a transition and the result of the transition is a logic level 1, then I'm going to do something. So this entire statement inside of the if statement here checks to see if I'm at a rising edge of my clock signal. So I can say if clock dash event and clock equal 1, then, well, my Q is going to be assigned the value of D. Okay, so I'm just going to add this comment here, and I'm just going to say if rising edge of clock. All right, I'm going to end off my if statement there, and essentially that takes care of the process for the D flip-flop. Just as before, all other conditions which would typically fall under an else block are accounted for by me not specifying an else block there. In other words, if I am not at a rising edge, then there's no change in Q, and Q retains its previous value. All right? And this is essentially the code for a 1-bit rising edge triggered D flip-flop. The alternative code for this for a falling edge flip-flop is shown in this slide here. All right, so you'd notice that I'm just checking to see if I'm at a clock transition that results in a 0. In other words, if I'm at a falling edge, then I'm going to assign the value of D to Q. Okay, so quickly reading from this script here, it says that the sensitivity list for each architecture contains the clock signal only. Notice how a rising or falling edge is determined. The /event keyword means a change in a digital signal that is an edge. When combined with a 1, a rising edge is defined. Similarly, when combined with a 0, a falling edge is defined. Now I specified that we also have alternative methods to decide if I'm at a rising edge or a falling edge. So, well, before I show you this, let me actually save this file and add it to my project. And I'm going to click on the Save button at the top here. And you'd notice that VHDL actually, Quartus, sorry, does not actually specify the name of the file for you here. So just to ensure that I'm matching the name of my entity, I'm going to name the file the same as the entity, which in this case is D_flip-flop. Ensure that VHDL files is selected and ensure that the add files to current project checkbox is checked. I'm going to click save, and to verify that the file was added to the project, I'm going to click on my files tab, and you'd see that I now have those two files there. All right. Okay. So the alternative way of checking a rising edge, and I'm going to remove the if condition here, is I can use a built-in function in VHDL called rising edge. So I'm going to type if rising underscore edge and the signal that I want to check, right? Then I'm going to do this. Okay. Now rising underscore edge is a built-in function that checks the rising or falling, the rising edge of a particular signal. The falling edge equivalent of this is simply if falling edge, and in brackets after the function name I can specify the signal that I want to check. So whether or not you choose to use the rising and falling edge functions, or if you choose to use clock-event and clock=1, that is a matter of personal preference. There's no difference in performance there. Okay, personally, because I learned it like this, I am just going to say if clock-event and clock=1. All right, and that's just because I learned to write code for rising edges like this. So to ensure that everything is correct here inside of this code, I want to save it and then compile it. Remember, when we're compiling our code, we click on the little play button at the top here, or I can double click on compile design on the left hand side of the window there. All right. Now, once you see that progress bar on your tasks window, you'll know that the syntax was correct, okay? Because by now, if there was an error, the compilation process would have halted and you would have seen the errors written in red on the output window below here. All right. Okay. So the functions, if you wish to use it, are also specified in the lab script here. All right. Now, there's an alternative way to check for a rising edge for my in my flip-flop circuit, and that is actually listed in the script here. Now, I'm not going to type this in my code here, but we notice that this process now uses wait statements here, and in using a wait statement, notice that I no longer have a sensitivity list because my wait statements will clash with my sensitivity list and you'll run into an error. And the reason for this is that your sensitivity list makes the process sensitive to certain signals. Alternatively, wait statements halt a process. And what this is essentially saying is wait until this change in clock occurs. And if your wait statement will cause the process to become dormant, then while it's waiting until there's a change in that signal, it's equivalent to a sensitivity list. So the wait until there is equivalent to you having a sensitivity list in your project. All right? Okay, so we've compiled the project, ensured that everything was as expected. And now what we'd like to do is simulate the behavior of these circuits. So what I want to do is I'd like to write a test bench for the D latch, and I'd like to write a test bench for the D flip-flop. Now the good thing is that just as in the timing diagrams that I had in the figures in the lab script, we can use the same test bench for both entities, all right, or for both circuits. And the reason I could do this is because my test bench is only generating that clock signal and it's only generating the input value D. The output value Q changes based on how the architecture that we wrote here processes those inputs clock and D. And the other reason that I can use the same test bench for both of these circuit designs for the latch and the flip-flop is we notice that the latch and the flip-flop both have the same overall structure in terms of two STD logic inputs and one STD logic output. And even more so, these inputs and outputs actually have the same name. All right. So remember that a test bench is essentially a VHDL file. And in order to write code for this test bench, all I need to do is add a new VHDL file to my project. Remember, to add a new file to your project, you can click on the new file icon in the top left hand corner here, and the new file dialog window that pops up, you can select VHDL file from the down drop and click OK. And this gives you this blank text editor area here to write your test bench. All right. Now, the lab script itself actually has all of the code to write the test bench, but it does not explain the process of creating this test bench, adding it to your project, and configuring the workspace to generate the stimuli for the test bench and launch model sim. And the reason for that is all of those steps were outlined in detail in lab 1. So the intention is for you to have understood the process of writing test benches from the lab 1 script and apply that theory to writing a test bench for lab 2. Now, again, I understand that we've only had 2 practical sessions. We've not had much practice in writing test benches, so I'm going to go through these steps in detail, right? So the first step we just completed was to add my test bench to my project. Well, to add a new file, sorry, to the project. And I'm going to write the typical 2 first lines here to specify the library and the package. And once I have these 2 lines here, I can save my file and add it to my project. I do this by clicking on the Save button from the taskbar, and the window is going to take me to the default folder. And in this folder, I want to specify the name of my test bench as d_latch_ff_tb. And you have the liberty to name the test bench file whatever you want. I'm just going to quickly show you the rationale behind my naming. I'm writing a test bench for a D latch, and I'm writing the test bench for a D flip-flop or FF, right? Pretty simple. So ensure that the file type is selected as VHDL file and that the checkbox add file to current project is checked, and you can click save. To verify that the file does exist in your project, you can select the Files tab from the Project Navigator window, and you'll see that the file has been added to your project there. All right. Okay, now remember, a test bench is just a VHDL construct. And what that means is that I'm going to now write a design file with a VHDL construct which consists of an entity and an architecture. But the important thing to remember is that a test bench entity has no input or output ports. A test bench is simply a body that generates stimuli in the form of VHDL signals. So to write this empty entity, I'm just going to type my entity keyword, give the entity the same name as the file itself, just to make life a little easy in case I run into any clashes. And after the is keyword, I'm going to write end entity d underscore latch underscore ff underscore tb semicolon. All right, and that is how you write an empty entity for a test bench. As always, with every entity that you write, you must have an architecture. And in the architecture body of a test bench is where I specify the generation of the stimuli that is going to simulate the entities that like the D latch and the D flip-flop. Okay, I can name my architecture TB, which stands for test bench, because I'm writing the architecture for a test bench. And of course, I need to specify that it belongs to the entity defined above. And in the architecture declaration section, I would like to declare the component, and I'd like to declare my signals. Remember, to write comments, sorry, it's 2 hyphens, and you know it's a comment because the text is highlighted in green. All right, so what I can do now is, well, what I need to do actually is, when you are writing a test bench, remember we are generating stimuli for some previously created entity. In this case, that entity is the D latch at first. To make reference to the entity in this separate VHDL file, I need to use the structural approach now, which is to declare a component here and ensure that that component corresponds to the D latch entity in the other file. To do this, I use the component keyword. I specify the name of the entity in the separate file. I need to ensure that this is typed exactly as is. And I need to specify the ports of that entity exactly as they are listed here. They need to be in the same order as they are written here. And for example, D must come before clock instead of clock before D. And I need to ensure that the data types match accordingly. So I'm going to write port D, comma, clock in std logic, semicolon, together with the output. And again, it's the same as before. If you want to make life a little easy, what you can do is simply highlight these 2 lines, copy it, and paste it inside of here. Okay, I suggest not doing that just yet because it's important for us to get the practice of declaring these components here. Once you've specified the input-output ports of the component, which corresponds to the entity in the separate VHDL file, you type the end component keywords. Again, I do not need to write the D underscore latch name there when declaring a component. The end statement is simply end component. All right. The stimuli are generated in the test bench in the form of signals because this entity is empty. The test bench body itself does not have output ports. So what we're going to do is create some VHDL signals that we are going to map to the D, clock, and Q ports of the D latch entity. These are signals, we can think of them as wires, which means that I don't need to specify whether they are inputs or outputs. Because all of these signals are of the same type std underscore logic, I can declare all of them on the same line using the same signal keyword. If they were of different data types, for example, a standard logic vector, then I'd need to use a separate signal keyword to declare that particular signal. Okay? So that takes care of our architecture declaration section, which means that now I can have my begin keyword here. And just to make sure I'm ending things off properly, I'm going to just write the end TB keyword there. All right. Now, at the beginning of this video, and even when we looked at lecture 9 in class, we stated that we actually have seen sequential VHDL before. And we've seen this in the form of writing the test bench for lab 1, when we were writing a test bench to simulate the operation of a simple logic gate. All right. So in writing sequential VHDL here, we know that sequential VHDL means by default a process block. And essentially, my test bench consists of processes which are generating the stimuli using these signals that are declared here. All right? So what I'm going to be doing is writing some processes inside of this test bench to generate the clock waveform and to generate the data input or D waveform. However, before I do this, remember that I need to make sure that these signals that the test bench is generating are mapped to the component itself. And I need to do this by instantiating the component dlatch. To instantiate a component, you give the instance a name. The standard for a test bench is to specify UUT or unit under test, type a colon there, and retype the name of the component that you have declared above. After you've specified the instance name of the component, you need to do your port map, which involves mapping the signals in the VHDL file to the ports of the component, which corresponds to the ports of the entity in the separate VHDL file. All right, so here now, to make life easy, I created these signals with the same names as the port names. So all I need to do is specify that signal D is mapping to port D, comma, not a semicolon, clock maps to clock, and Q maps to Q. No comma here because this is the last one, and well, there's just the close brackets and the semicolon after that. And that takes care of creating an instance of the component. Now that I've created the instance of the component, I can write these processes now to generate the signals for D and clock and observe the signal of the output Q in the test bench using the model sim software. All right. Now, we stated that all code between or within the begin and end keywords of a process is sequential. All of the code inside of a process is sequential. However, everything outside of a process occurs concurrently to one another, which means that if I have multiple processes, one to generate a clock signal and one to generate the input waveform, then those processes will be executing concurrently to one another. So let me now create the first process for generating the clock signal. Because I'm going to have two processes inside of this architecture, I can now name my processes to distinguish and add some more some more understanding for the code itself. Okay, so my first process, which is going to be generating the clock, I'm going to call that clock proc. All right, and for those of you who remember, the processes in a test bench are always written using wait statements. And what that means is that if I'm using wait statements, I cannot have a sensitivity list as we covered earlier today. All right. So I'm writing my begin and end keywords for my process here. Right. Some things to note. The line on which you declare the process does not end with a semicolon, and the line with your begin keyword, just as with an architecture, does not end with a semicolon. All right. Okay. Now I'm taking the signal that I declared here, which is clock, and I'm going to assign to it a bit value of 0. Then I'm going to specify with the wait keywords, wait for 20 nanoseconds. Then I am going to assign a bit value of 1 to the clock and tell it to wait again for 20 nanoseconds. All right? And what this is doing now is this process is going to be continuously repeating line by line over and over again because because it does not have a sensitivity list, it only halts at the wait statements and it's not waiting for a signal to change in order to be reawakened. Instead, it's waiting for a particular time. And from the time that I specified here, 20 seconds off, 20 seconds on, 20 off, 20 on, 20 on, 20 off, 20 on, that implies that the period of this clock wave is now 40 nanoseconds. All right, because it's off for 20 and it's on for 20. So the full waveform or the period will take 40 nanoseconds. And of course, once I name my process, I want to just rewrite the name on the end process keyword line there. Okay, and that's it. I've created the process for generating a clock waveform. The next thing I want to do now is generate a create a process, to generate a waveform for the data input that is a kind of haphazard waveform that looks something like this. All right, and what I'm going to do here now is I can name this the input process. Again, no sensitivity list, right? And inside of these begin and end keywords now, I'm just going to say D is equal to 0 initially, and I'm going to wait now for some random times. All right, then I can say D is assigned a value of 1, and I can wait for, again, some random times. And what I can do now is I can highlight these statements, copy and paste them a couple times, right? Please note how you're copying and pasting so that things will go on different lines. And I can change up these times a little bit here to make it a little interesting to generate a haphazard statement. Okay, so I'm going to wait for 25 nanoseconds there. I'm going to wait for maybe 50 nanoseconds. Well, I can wait for 15 nanoseconds here. I'm going to wait for 50 here. And I'm going to wait for 20 nanoseconds here. All right. Now, what happens in this process is that it's going to generate 0, 1, 0, 1, 0, 1 for all the specified times. And when we reach this line here, it's going to restart the process from the first line here. If you want to halt the process such that it no longer repeats this pattern with these different times, you can just place one wait statement at the end of the process, and that is going to halt the process indefinitely after we hit this line here. Okay, if however you do want a repeating signal, then you will omit this statement here. All right, now that I've written the test bench, that's the end of the test bench file there, I want to make sure I save it, and I would like to compile this to make sure that I have no syntax errors inside of that test bench VHDL file there, and it would seem that I have an error somewhere here. Let's see if we can spot the error here. Well, it tells me that near line 53, near the text end, we don't know if it's this end or this end, but it's telling me that I am missing a semicolon. And as we know, our end process lines should have semicolons at the end of them. And of course, I just want to, for good programming practice sake, restate the name of the process itself. So let's save and compile this now. Remember, the compile button is the little play button at the top here, or you can select processing, start compilation. All right, so I'm going to compile this code file again, and I noticed that once the progress bar starts moving here, I don't have any syntax errors there. So what it's doing now is it's synthesizing the underlying circuits for me. Okay, now once this is finished compiling, we need to set up the Quartus II environment to be able to call the simulation software, which is, of course, Model Sim Altera. To do this, we have to follow some simple steps, which again are stated in the Lab 1 script, but I'm going to repeat them here for the sake of completeness. All right. The first thing I want to do is ensure that the model sim path is specified as the simulation tools path. To do this, from the menu bar, I'm going to select Tools. I'm going to go down and select Options. And in the right-hand side of the window here, where it says Category, I am going to select EDA Tool Options under the General downdrop. And I'm going to ensure that the ModelSim Altera text box is set as the path for the path in which ModelSim is installed. If you do not see a path here right now, then I need you to click on the Browse button and navigate to the folder where ModelSim is installed. And this is Altera 13.1 ModelSim underscore ASE AL OEM, Win32 ALOEM, and that is the folder there. So once you have selected Win32 ALOEM, do not select any of these folders, and ensuring that Win32 ALOEM is in the folder text box here, click Select Folder. Now, this may not work, and if it does not work in the end, just to ensure that it works properly, let's just add an additional backslash. That's the key above your Enter key on your keyboard. Let's add that backslash to the end of this statement here, and we'll click OK. So that takes care of the Quartus II software being able to find the path in which the simulation software is installed. The next thing we need to do is to specify that the test bench file that we just wrote, that's this test bench file here, I need to specify that it is indeed a test bench file for this project. Now to do this, we are going to go from the menu bar to the Assignments option on the menu bar, and we're going to select the second option from this menu, which is Settings. And again, the category window on the left-hand side, under EDA Tool Settings, I want you to select Simulation. All right. Ensure that the radio button or the checkbox Compile Test Bench is selected. And under this downdrop here, you may not see anything. I already have mine set up. But what I want you to do now is click on the Test Benches button on the right-hand side there. Okay, and you'll see a window that says Test Benches looking something like this. And currently, what this is stating is that I have no test bench files added in my project. Now, I had one before. I just deleted it there to show you what your window should look like. In order to add, or rather in order to specify that the VHDL file we just coded is a test bench, I need to add that to this test bench window. I'm going to do this by clicking on the New button on the right-hand side, and on the new test bench settings window that pops up, I'm going to give my test bench a name. In this case, I can call it the same thing, d_latch_ff_tb. All right. And in the file name section here at the bottom, under the section that says test bench and simulation files, follow my mouse. I need you to click on the ellipsis or the browse button here, and the select file dialog window that pops up here, I need you to select the actual VHDL file that contains the test bench code. And that is, for our purposes, d_latch_ff_tb.vhd. Do not select the file that says .vhd.bak if you do have that file. We want to select the file that says .vhd. I'm going to click Open, and the file name has now been specified here. In order to add the file as a test bench file, I'm going to click Add, and you'll notice that the file now exists in this little area here. Once that is present in that area, I'm going to click OK, and you'll notice now that the test bench file is also in this test benches window here. Before we can continue, you need to ensure that you have a test bench file in this window. As long as all this stuff is set up, you can click OK, And you'll notice that the test bench is now listed in the down drop here. Click Apply and then click OK. Feel free to pause and rewind that part of the video as much as possible to ensure that you are comfortable with creating and adding a test bench file to your project and further specifying that the test bench file is linked to this project. All right? After doing all that, we need to recompile the project now that we've configured the test bench settings. To do this, again, I can click on the compile button, or I can double click on compile design on the left-hand side there. All right. Now, at this point, we've added this test bench file. We've specified that it is a test bench file to test our Latch circuit, and we've specified the path of our Model Sim Altera simulation software. Once the compilation is successful, we can now launch the Model Sim tool by clicking on this little button here. That's to the right of this clock symbol here that says RTL simulation. Alternatively, you can click on Tools, Run Simulation Tool, and RTL Simulation from your menu bar. Okay, I'm going to click on RTL Simulation, and assuming that you have the Model Sim path set up correctly, you should see Model Sim opening like this. If at this point you do get an error message, then please note that you need to specify the path with the backslash in the options window, in the tools options window. Again, you can pause and rewind the video to do that. All right. Now, I have here the Model Sim window popping up. Model Sim is a little tricky in that sometimes you may see a waveform appearing one time and it's generated by default. And in this case, my waveform is currently not generated. Okay? Or rather, it's being generated as we speak. How I know it's being generated is I can look at these waveforms here in this right-hand portion of the window here with my clock signal, my D signal, and my Q output signal. And this little green bar that's increasing in size there is actually a zoomed out version of the clock signal that's being generated. So from the taskbar above, there are some zoom buttons at the top here that the mouse is currently hovering over. What you can do is keep clicking the zoom in button, and you can click the stop button here to stop your simulation. All right. And what you can do is this yellow marker, when you click on the black area of the waveform, you can drag this yellow marker as you see fit. Now, the waveform, the clock waveform, the D and Q waveforms have been simulating for some time. Okay, we knew that we wrote this test bench to do something to the order of tens of milliseconds. But if I look at the nanosecond, the timestamp bar at the bottom here, I'd see that some tens or hundreds of millions of nanoseconds have elapsed. If I look at below that bar now, there's a left to right scroll bar here that allows me to kind of look through all of the simulations that have gone thus far. So what I'm going to do is I'm going to take this scroll bar and drag it all the way to the left to get to the beginning of that waveform where I was generating the signals Q and from D and clock in my first, say, 100 nanoseconds or so. And this portion of the waveform here is where I see D and Q changing as I set it to change. Once I place my marker, the yellow marker, in this area here, I can click on the zoom in button. And if this happens, it may take you somewhere a little off. You can just drag this all the way to the left again and you get to the respective point. Now, look at the order of the waveforms here. Actually, I'm going to zoom out a little bit. Look at the order of the waveforms here. My clock waveform is second in the line, and if I want to make it a little closer to this timing diagram here, then all I can do is click on clock, hold it, and drag it up to the first section, like this, so that my clock waveform is now at the top. Okay, and then I have the D waveform and the Q waveform, and this may make it a little easier for us. Now let's verify that the D-latch circuit operates as expected. Okay, well, in the initial stages, when my clock signal is 0, you'll notice that the output Q has this little red area here, this red bar here. And what that means is that Q is currently undefined. If I drag the marker to that section of the waveform, you'll see that the waveform Q has a value of U in this waveform window to the left-hand side here. All right, and that simply means undefined while values of clock and D are 0. When my clock signal goes high, D is still low. So my output Q now becomes 0. It goes from undefined to 0 because remember, before when clock was 0, Q would not see the value of D. Q will only see the value of D when the clock is high. For the duration of time that this clock signal is high, you'll see that the D input goes high, and that change is reflected in Q almost instantaneously. In other words, Q automatically goes high there. D remains high for the rest of the period until the next period here when D is high, Q is still high. For the duration of time while the clock was low, Q had retained its previous value of high over there. Again, the input D changes while my clock signal is high, and that change is reflected in Q instantaneously. For the duration of time while the clock period is low, note that D changes while the clock is low. At this point here, let me zoom in a little bit here. That's at this point here. When the clock is low, D goes from low to high. But notice that my Q output is still low because Q is retaining its previous value while the clock is low. Q only goes from low to high when the clock goes high. And again, for the duration of time while this clock is high, signal D changes, and as such, signal Q changes accordingly. Likewise, D changes at this point here when the clock goes low. Because D changes as soon as the clock goes low, that change is not reflected in Q in this area here, and I'm highlighting the area with the yellow marker, which means that Q retained its previous value of 0 from before. When the clock signal goes high again, Q changes to 1 because from then onward, D remains at high. Notice that the waveform D remains at high here and is not repeating because of this final wait statement here. All right, going back to model sim now. The clock waveform repeats in its on-off manner because I didn't have one single wait statement to halt that process, which means that this process is continually executing and generating that clock signal all the time. All right. The last thing I want to take care of here is let's look at the waveform D and Q. D is low, then high, then low, then high here, then high again. You'll notice that the Q waveform is also in a similar pattern: high, low, then high again. However, in this case here, the input waveform is delayed a little bit, and likewise in this part of the waveform here, the output is delayed a little bit. And that is the purpose of the D latch. It's a delay latch. In other words, it delays the signal by a little bit. Okay. However, at the end of the day, the pattern of the waveform is the same. And because the pattern of the output waveform is essentially the same as the pattern of the input waveform, that is what we refer to as a D-latch, or sequential code exhibiting memory. The fact that it keeps that state there reiterates the concept of state or memory in some sequential circuit. So what I'd like to do now is close off model sim here. All right, and I'm going to go back to the Quartus II environment now, and I'm going to configure this test bench a little bit to work with the D flip-flop component. And because the D flip-flop entity had the same inputs and outputs, same number of inputs, same number of outputs and same data type of the inputs and outputs as the D latch, then all I can do is change the component name here of D latch to flip-flop, ensuring that the name matches here exactly. All right. And when I'm instantiating the component here, I need to ensure that I instantiate something that was declared above. So I'm going to change the instance of the unit under test component to D flip-flop. All right. And that's all I need to change. The waveform is going to be the stimuli that I'm generating is going to be the same. I can save and compile this project. And then when I open ModelSim again, we are going to notice a change in the output waveform such that the output waveform is now more synchronized and a lot more in time, and the changes only occur on my rising edges because the architecture of the D flip-flop occurred for Q being assigned the value of D on the rising edge. All right, so the circuit has been compiled. I'm going to open my simulation tool again by clicking on the RTL simulation button from the taskbar. We see that ModelSim is opening again. All right, and again, assuming that you've set up everything correctly, the waveform should generate automatically. If the waveform does not generate automatically, there are some troubleshooting steps in the Lab 1 script. All right, now once I place the marker in this area here by clicking in the waveform window, I can click on the blue magnifying glass that says zoom full. And once you click zoom full, you'll see the little waveform there. That's the clock waveform being generated. All right. We can zoom in all the way by clicking multiple times on the zoom button. And I can click stop. And I can go all the way to the right now. And let's see what's going on here now. We notice that the waveform is not being generated for the output here. All right, let me just add this Q signal up there. Let's see why that is. Well, it may be because the test bench is still recognizing the inputs from the D latch. We need to set the D flip-flop as the top level design entity. So in the Files tab of your Project Navigator window, you're going to click on flip-flop, right-click, and set as top level design entity. And you'd notice that back in the hierarchy window now, D flip-flop is set as your top level design entity. Recompile your project, and that should be the solution to that problem there now. Because what happens is the test bench was being run on the top level design entity, which is why it was combining the test bench with the D latch entity VHDL construct. Okay, so once I run this here now, just to verify that the file works as expected, okay, if I click on zoom all, stop this, and I'm gonna zoom all the way there now, and now we have a value for Q. I'm going to scroll all the way to the left, and now we can observe the operation of the D flip-flop. All right, so on the rising edge of the clock, let me just place the clock signal on top again by clicking, holding, dragging, and dropping. All right, when the clock signal is high, the value of D gets translated to Q on the rising edge. The input signal D changes while the clock signal is high, but that change is not reflected in the output Q here because that change does not occur at a rising edge. That value of D remains high until the next rising edge, and as such, that value of D is translated to Q at the rising edge there. Okay, D goes low for the rest of the duration of the period here, and that is not reflected in Q at all. In other words, Q was assigned the value of 1 here, and it held on to that value until the next rising edge. And the next rising edge just happened to be a value of D having logic level 1, which means that for the rest of the duration of that clock signal, Q also remained high. At this point here, by this rising edge of the clock signal, D is now low. So note the time it took for that value of D, that low value of D, to translate to the output. That's from all the way here to this next rising edge here. And what that means is that the data signal that's being forced into the input there is translated to Q, but it now becomes synchronized to the clock signal because of that rising edge feature that we added in the architecture body there. The circuit still exhibits memory, but instead of taking changes from high, low to high to low to high, we simply have low to high to low to high. So we miss this little blip in the middle here. And something like that is actually used to our advantage if we want to filter noise or jitter out of the memory circuit. So that takes care of simulating the test bench there. All right, you can follow along on the script here as usual, and we are gonna move on to the next topic now, which is writing code for the full D flip-flop circuit. All right, now remember I stated that we were looking at simplified versions of the D latch and the D flip-flop. From now on, we are going to be focusing mainly on D flip-flops, because any question that you'd get in an exam would only ask you to write code for a D flip-flop, be it handwritten code or typed code for your practical part of the exam. All right. Now, typically, the full D flip-flop, well, at least the full 1D flip-flop, has an additional input, which is simply a reset input. And what that reset input does is, depending on if when the reset button is pressed, essentially, we want to just set the output of Q to 0. And what that means is that that reset signal is going to have preference over the clock signal. All right, so what we need to do now is we need to modify our D flip-flop circuit, or rather we could actually just create a new flip-flop circuit altogether. All right, so that we can test that other circuit separate. So let's add a new VHDL file to our project. I'm gonna click OK. I'm gonna write my basic stuff here. Right, and again, guys, sorry about the noise. I live close to the highway, and it's starting to rush hour is starting soon. All right. Okay, let me save this file, and I'm gonna save this one as full DFF. All right. Actually, I'm gonna save it as full 1-bit DFF because it's still a 1-bit D flip-flop here. All right. I'm going to write the entity, and again, I typically want to make things uniform. I want to keep the name of the entity the same as the file name. So full underscore 1-bit underscore DFF is my entity. And the port now is going to include a 1-bit reset signal. So my inputs are still going to be D clock, and now this third input, reset, again of type std underscore logic. And my output is still Q. All right. Now, one thing to note about the reset signal is that the reset signal can be active high or active low. And that is just terminology for if the reset signal is 1, it can reset the circuit, or if the reset signal is 0, it can reset the circuit. If the reset signal resets the circuit when it is high, we refer to it as an active high reset. If the reset signal is low, if the reset signal resets the circuit when it is low or 0, we refer to that as an active low reset. In addition to that, we can have asynchronous resets, And we can have synchronous resets. An asynchronous reset resets the output Q regardless of the value of the clock. A synchronous reset resets the output in tandem with the clock signal. In other words, a synchronous reset is governed by the clock, whereas an asynchronous reset acts independently of the clock. Now that the entity has been created here, I can write my architecture, and I'm going to say the architecture now is again a behavioral architecture, and it's of this full 1-bit D flip-flop entity. All right, and what I'm doing in this architecture here now is I'm going to say my process, which is now sensitive to the clock signal and the reset signal, right? Okay, so the first thing I want to do, as always, well, rather, let's, for now, we're going to stick with an active high reset, an active high asynchronous reset. Okay, and it's important for you to know these terms active high and asynchronous, because a question in an end of term exam will specify whether it should be synchronous or asynchronous and whether it should be active high or active low. Your reset signal is always a 1-bit signal. So what we want to do is we're going to use an asynchronous reset signal that is active high. So what I can do is I can check if reset is high, then Q is going to be low. All right? And we notice that at this point here, I'm letting the reset signal take priority or precedence over the clock signal, which implies that it is asynchronous and no longer governed by the clock. And to understand how it is independent of the clock, we need to understand how the if statements are written here. So I state if the reset is equal to 1, then I do that, else if, and then I go on to define my rising clock edge signal there. My rising clock edge statement, sorry. Okay, then Q is assigned the value of D. All right, so this is an asynchronous active high reset. Okay. If it were to be an active low reset, then the signal would be cleared, the output signal would be cleared when the reset signal is low. And this is now an active low reset. Okay, so keep that in mind there. So I'm going to stick with active high for now, and I'm going to stick with asynchronous. All right, we're going to write a test bench for this circuit, simulate this circuit, and then we are going to write the code for a synchronous reset. All right, so I'm going to write a separate test bench file for this code. Again, I'm adding a new file to my project, and what I can do is I can just take the code from the original flip-flop here, copy and paste it into my new VHDL file, and just ensure that I change some things accordingly. So this one is going to be my full underscore D flip-flop TB. All right. Now, I cannot have two entities of the same name. The test bench is an entity in its own right. So I'm going to rename my entity full underscore DFF underscore TB. I'm going to copy this name and I'm going to paste it at the end entity line, and I need to ensure that I paste it between the of and is keywords of the architecture declaration line here, because I'm now writing a new architecture for a new entity, right? The entity that I am simulating is now the full underscore 1-bit underscore D flip-flop. So I'm going to copy this line here, and I'm going to specify that as the component that I am simulating here. Okay? Note that the port of the component here must match the ports inside of here. And in the full flip-flop, I now have this added reset signal here. So in the port of the component declaration section, I'm going to add in reset, ensuring that I spell it exactly as it's spelled here. In my case, I have a capital R, so in this case, I'm going to put a capital R. Now, I'm doing a little bit of a shortcut here by copying and pasting. I urge you all to be very, very, very careful when you're copying and pasting documents like these, okay? The reason I'm going through the copy and pasting is I know that it is unavoidable for some of you to do that, and you think that it's the easy way out. So to show you how to correctly take the easy way out, I'm doing that now, okay? I'm also going to add a reset signal in my list of signals. I can add it to the same line of this signal declaration line because it's of the same data type here. I'm going to remove this component instantiation completely, and I'm going to rewrite the component instantiation here. Okay, so instantiate component, and the reason I'm doing this is I want to make sure that I don't mix up anything with my port mapping. All right, it's still the unit under test, and I'm gonna specify that the unit under test belongs to the component that I specified above, full_1bit_d flip-flop, not full_dff_tb. We are instantiating the component based on the component defined in this section here. After I create the instance of the component, I want to do my port map by specifying signal D is mapped to signal D. The signal clock is mapped to the input clock. The signal reset is mapped to the input reset. And the signal Q is mapped to the signal Q. Note that I'm doing it all in one line, in this case separated by commas. If you wish, you can do it on separate lines to make things a little more readable for you. That is simply a matter of personal preference. All right. After making all the changes with the name of the entity, the name of the component, and the instantiation and port mapping of the component, everything else essentially remains the same because I'm generating the same signals here. What I do want to do, however, is now create a third process that's going to generate a reset stimulus. So I'm naming this process here. Just going to type in my begin and end keywords, and all I want to do is say that the reset signal is equal to 1, because remember it's an active high reset, and I'm going to wait for, say, 60 nanoseconds, and I'm going to leave it long deliberately so that I get so that I can see the change there. I'm then going to deactivate the reset signal, and instead of typing wait for, I'm going to type wait, which implies that the reset signal is going to remain at 0 until the end of the simulation. So I can save this file now. I can compile the design to ensure that everything was typed correctly inside of here, and we see that I have a minor little error here. Okay, and this is one of the things that will happen when you are copying and pasting code and stuff, right? In this case, my error was in my VHDL file. I forgot to put my end if statement here, so I'm going to save and recompile. Hopefully that fixes everything. So it seems to be compiling there. All right, now remember, this is a new test bench file, which means that I need to go over the entire process of adding and setting up a test bench file in the Quartus II settings itself, okay? So this is actually good practice for us to get accustomed to the process of setting up a test bench. So I'm going to go to Assignments from the menu bar at the top, select Settings. Under EDA Tool Settings, I'm going to select Simulation, and we see in the down drop here the previously created test bench is set here. But I'm no longer using this test bench because this test bench will not be testing the reset signal. So what I need to do is click on test benches, and I'm going to add a new test bench file to this list of test benches here. I'm going to select new. And I'm going to name this test bench full underscore 1-bit underscore DFF underscore TB. And in the file name window at the bottom of this new test bench settings window, I'm going to click the browse button. I'm going to select the newly created test bench file, which was full underscore DFF underscore TB. I'm going to click open. I'm going to click add so that I can add it as a test bench file, and click OK. And from the down drop now, I want to ensure that I select the appropriate test bench. Once selected from the down drop, click apply, then click OK. Again, feel free to pause and rewind the video so that you can do this step by step at your own pace. Once this is done, I'm going to recompile my project, and everything should be set up for the Model Sim tool. Actually, no, it would not be set up, because the last thing I want to do is just set the newly created 1-bit D flip-flop as the top level design entity. Okay, so to do this, I'm going to click on the Files tab here. I'm going to highlight full underscore 1-bit underscore DFF, which is the entity architecture itself. Right click on that and select Set as Top Level Design Entity. To ensure that it was set up correctly, I'm going to click on the Hierarchy tab and ensure that the top level design entity is currently full underscore 1-bit underscore DFF. After I do this, I actually need to recompile the project again before I can open Model Sim. So you see how many steps there are involved for you to do this. The quicker and the faster you get accustomed to these steps in the initial baby step stages here, the easier it will be for you for your design project, and the easier it will be for you for writing and creating test benches and waveforms for final exams. Okay, so the compilation was successful. I'm going to launch my Model Sim tool here. All right, and I should see the waveform being generated automatically, assuming that everything was set up correctly. Again, if yours does not generate automatically from the Lab 1 script, there are highlighted snippets and screenshots of the window telling you exactly how to set up the waveform. That's on pages 25 to 28 of the lab script there, lab 1 lab script. Okay, so going back to Model Sim now, I'm going to place my marker in the window, and as a matter of fact, we see that the waveform is not generated automatically. So this is actually now good practice for us to add a waveform, add a test bench and entity architecture file manually. Okay, to do this, in the library section of the left hand pane of this window, I'm going to expand on the down drop by clicking on the plus sign by the word work. I'm going to click on this first entity file once. I'm going to hold my shift key on my keyboard and click on the second file, and this is going to ensure that both files are selected correctly. Right click on the highlighted files, and I'm going to select recompile. Okay, and assuming that everything occurred correctly here, you should see something like this at the bottom of the transcript window here. So let's see if this works now. Going to right click again on the highlighted files and select simulate, and we see that the waveforms were added in the objects window here now. I'm going to click on one of the waveforms. I'm going to hold my shift key again, and I'm going to click on the last waveform there, which is Q. I'm going to right click on these highlighted objects, and I'm going to select add wave from the menu bar there. Okay, and this is good practice for the manual setting up of a test bench file. Now I need to set the time scale for my test bench. So let's look at this here. I'm going to go back to the test bench file in Quartus, and I see that I'm generating a clock and an input signal for some, say, 30 plus 7 plus 40, 70, 95, 105, 110, 160, 180 nanoseconds ish. So I can now generate a waveform for 200 nanoseconds. And I do this by highlighting the text in this little window. Look at where my mouse is hovering at the top here. I'm going to highlight that text, click backspace, and I'm going to type in 200 ns, which stands for 200 nanoseconds. After I do that, the little white page just to the right of that, if I hover over that with my mouse, you'll see that the label that pops up is run. I'm going to click run. And I would like to just see what's going on here. All right, so we have some undefined things going on here now. If I run, keep running again a little bit. Okay. So now I'm going to break this, rerun it again. And it seems that there seems to be a problem in the design in some way. So let's go back to the lab script for lab 1 and see how we're going to do this. We can select recompile, start simulation. Yes, you need to select the test bench file explicitly. Okay, so let me just redo these steps again. I'm going to highlight these files in the library window, right click, recompile them. Then going to, from the menu bar, select simulate, start simulation, and I'll expand the work down drop here, select the test bench file, click OK, and that should take care of everything there. I'm gonna just add my time scale again, click simulate those values, and add these waveforms to the window here. We simulate this one more time, and that should take care of everything there. I'm going to scroll all the way to the left by dragging the scroll button to the left. Let me just find the appropriate signal. Right. So dealing with all this stuff and troubleshooting all this stuff is just a matter of playing up with the environment and knowing exactly how this stuff works out. Okay, now at this point in time, what's happening here? Let me just quickly restart the simulation. Okay. All right. So I'm going to place my clock signal at the top. I'm going to place my reset signal here. And it seems as though for the first, there we go. If I scroll to the left now, I can see the waveform. So let me zoom in a little bit, scroll to the left, and observe what happens here. Okay, now I dragged and dropped my signals a little bit by clicking them here and dragging and dropping. I have the clock signal first, then my reset signal. So look at when the reset signal is high, what happens. That's for this duration here. Despite the fact that I hit a rising edge and that the output of D changes here, the value of Q remains 0 because that reset signal is high. At the rising edge here, Q takes the value of D. The change in D here is not reflected because at the next rising edge here, I have this signal D being high, so Q remains high for the duration of that time there, because as long as I'm not at a rising edge, Q retained its previous value here. Then at this rising edge, Q is actually being assigned D again, but D was high at this point, so it looks as though Q just remains high throughout. At this rising edge here, my reset signal is low and my D flip-flop signal is low, and the clock signal is at a rising edge, so the output was translated, the input was translated to the output. So you see how the values change there. I urge you all to alter these times in your test benches a little bit and manipulate this a little bit to get different waveforms so that you can understand the logic there. All right. Okay, gonna close off model sim again, and now I'm going to modify the 1-bit D flip-flop now to try something else. I'm going to use an active low reset, and I'm going to ensure that it is a synchronous reset. Now we stated that the asynchronous reset was independent of the clock, which is why it had its own if statement by itself. A synchronous reset now, and I'm removing all those statements here, looks something like this. Because it is being governed by the clock, the first if statement that I'm having here is going to check for the rising edge of the clock. And within that if statement now, I would like to have something called a nested if statement that's going to check if reset is equal to 0. And now it's checking to see if reset is equal to 0, because when reset is equal to 0, that is when I would like to have my value of Q being reset to 0. If the reset is not 0, in other words, if the reset is high, because it's an active low reset now, then Q is going to be assigned the value of D. Now please pay attention to the syntax here. This nested if statement that exists inside of this if statement must have its own end if keyword. To make it a little more readable, I tabulated the text a little bit inward. All right. Each if statement that you have, or each if else statement that you have, must have a corresponding end if statement. So I have an end if statement inside here for this nested if statement, and I have an end if statement outside here for the outer if statement. And this is the syntax for writing a synchronous reset. If they had asked you in an exam to write an active high synchronous reset, then you'd simply change this reset value to a 1 here now. Okay? Now in this case, because the ports remain the same, I can actually use the same test bench to test this circuit. So let me quickly compile this design. All right? Make sure that there are no errors, which is why I compiled the first time around. And then, after this compilation is successful, I am going to just set this as actually it's already set as the top level design entity, so I don't need to do anything further there. Remember, I'm using the same test bench file corresponding to the same design file, so I don't need to change anything in the test bench settings. So I can just launch Model Sim now. And we should see some things happening here. If I do need to manually set up the waveforms again, well, we know how to do that. All right, so it seems that there's an error compiling the design, so we need to recompile this explicitly. Again, to do this, I expand the work option here, highlight both files, right-click, select recompile. Once compiled, I'm going to leave them highlighted, select simulate from the menu bar, select start simulation, and I expand the work option of the library here, select the test bench file, click, well, I can change the resolution actually of the timestamp now to 100 nanoseconds. I'm going to click OK, and I'm going to highlight my signals, sorry, right click and add waveforms for those signals, and then I can start simulating here. I start simulating by clicking the run simulation button that's my mouse is currently over. Run the simulation one more time, and it's zoomed out to the scale of microseconds. So to get to this area where the simulation exists, I take my marker, that's the yellow marker, I drag it all the way to the left-hand area of the screen, and I click the zoom in button multiple times until I see a waveform starting to form. Okay, let me just 10 microseconds. Let me just simulate this a little bit here. And I need to restart the simulation. I believe I do. So let me specify this to be 200 nanoseconds. Okay. Alright, so it seems as though it is not generating the test bench file. Let's just troubleshoot this really quickly. This is what I'm testing here. I'm testing this D flip-flop. Yeah, that's what I'm testing. Alright. And I am testing this test bench. The signals are mapped accordingly. It's just that I changed the implementation to active low and synchronous. Right? Actually, if I want, I can change this to 0 and 1 here, just so I can exhibit the active low statement there. Of course, as soon as I make a change here, I need to recompile it. And once it's recompiled, I'm going to start the simulation. And fingers crossed, hopefully it works at this point in time. Okay, and let's see what happens now. Okay, I'll recompile these files. Let me start the simulation, expand this, select the test bench accordingly, add it to the file. Okay, so we see the processes here. Hopefully it's registering the respective entity. Just ensure that the entity is there, yes. Okay. Add these signals as waveforms. I'm going to select a time scale of 100 well, select 200 nanoseconds, and then I am going to click simulate. And fingers crossed, it hopefully works now. Okay, all right. So if I click zoom all, we see that it works now accordingly. Honestly, not sure what was going on there, why it wasn't working. Okay, all right. Now while the signal is 0 here, notice that it is a synchronous reset. So the reset signal does not take effect. Let me just place these waveforms accordingly. I have my clock signal on top, my reset signal second. The reset signal does not take effect until the first rising clock edge here, which is why Q is undefined before the first rising clock edge at this point here. Okay? And of course, at this point here, the reset, the active low reset is low. So the 0 that we're seeing on the output here is not the value of Q being assigned the value of D, but rather it's a 0 because the reset signal was low. At this point here, when my reset signal goes high, that is when I start looking at the value of D being translated to the output Q. And as such, the waveform just continues as before. Okay, so note the difference between the synchronous reset and the asynchronous reset. Your synchronous reset, because it is governed by the clock signal, is going to give you this little undefined area in the beginning here. So that takes care of that for D flip-flops. The next topic that we're going to look at for the lab script is the topic of counters, and that is from page 12 onward. All right, now we looked at counters during the review lectures as well, as counters is ideally an electronics topic from year 2, the year 2 digital electronics course. So it was covered in the review lectures. All right. Again, I'm not going to go through in too much detail things like the diagrams, etc. But the lab script does give a quick little recap of exactly what a counter is. So it's a sequential circuit, and it states that the counter itself counts by one state for each clock pulse, okay? And the most important thing in that is that it counts in a predictable repeating pattern. For example, if I have a counter that counts from 0 to 9, I know that I will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back down to 0 and repeat that sequence. Okay? Now, the three types of counters that we'll be looking at today are binary counters, modulo n counters, and BCD counters. Okay, and we can also look at up counters, that is counters which count in an ascending order sequence, and we can look at down counters or counters which count in a descending sequence. All right, so the first thing we're going to look at is the binary counter. And just quickly reading from the script here. In an n-bit binary counter, there are 2 to the n possible values that can be represented, ranging from 0 to 2 to the power n minus 1. So what this means is that for a 4-bit binary counter, for example, I can represent values going from 0000 to 1111, or in other words, 0 to 2 to the power 4, which is 16, minus 1, which is 15. So that's 0 to 15, for a total of 2 to the power n, or 2 to the power 4, or 16 possible states. All right? If it were a 3-bit counter, then there would be 2 to the power 3, 8 possible states, counting from 0 to 7. All right? So the most basic counter we could look at here is an n-bit binary counter, going from 0 to 15, which is a 4-bit binary counter. Okay? Now, I'm going to add another VHDL file here to my project, just so I can write the code for this counter. Okay, so as always, I'm going to click on the new file icon and select VHDL file, click OK. And actually what I'm going to do is I'll just close off these tabs at the top here because I'm finished with the latches and flip-flops for now. Okay. As always, I'm typing my code here. And I'm going to start with the, I'm going to start with the std logic package. And now we're going to see the use of some additional packages here today when dealing with counters, okay? And what these packages are is essentially when we are counting in binary counters, we advance one state after the next. I go from 0, 1, 2, 3, 4, etc. And what that means is in each state, I'm going to be adding 1 to the current state in order to advance to the next state. And the additional library packages that I'm going to be using here to do this are the std logic arithmetic package and the std logic unsigned package. And this essentially allows me to perform basic arithmetic on unsigned logic vectors. Okay? So the packages of the IEEE library that I'm going to be adding are the std underscore logic underscore arithmetic package and the std underscore logic underscore unsigned package. When I say unsigned, remember that we looked at unsigned numbers versus signed numbers. This means that we are only dealing with bit representations of positive numbers, which means that we don't need to worry about things like 2's complement representations or signed magnitude bits, etc. Okay, now the counter advances on every clock cycle, and what this means is that I don't need any data inputs or anything of the sort. At least for a basic counter, I don't need any data inputs. So I can have a counter that just starts at 0, and on every rising edge of my clock, I'm going to advance from 0 to 1 to 2 to 3, etc. in some predictable repeating pattern. And additionally, what I could have is a reset signal to reset my clock. All right, so what this means is that my entity for this clock, this binary counter that I'm dealing with, is going to look something like this. So I'm going to name my entity binary counter. And let's take a look at the ports that I'm going to have here now. I'm going to have my clock and my reset. And these are, of course, 1-bit std logic values. And then I am going to also have my count out, rather I'll call it the output, okay? And that is my output. Sorry, this is the input. This is my output of type standard underscore logic underscore vector. And the reason it's going to be a vector is because, remember, I'm dealing now with 4-bit values. All right, so to specify that the vector is going to be 4 bits wide, I say that it's a vector going from 3 down to 0, where the leftmost bit is my most significant bit, as denoted with the down to statement. Okay. Now remember, I don't place the semicolon here. I place the close brackets corresponding to the port statement's opening bracket, not to be confused with the close brackets of the standard logic vector. Then I place my semicolon. Right? I end off this entity block here, and that takes care of defining the entity for this circuit that we would like to describe. Now I'm going to save this file, and I'm going to save it as binary counter in the same project folder. All right. And the next thing I'd like to do now is to write the architecture for this. All right. So the architecture corresponding to the entity, again, this is a behavioral architecture of the binary counter entity that I just created. And now I'd like to have some signal existing inside of the architecture. I'm going to name that signal count, and I'm going to make it a 4-bit vector. And I'm going to use this count signal to manipulate the actual counting, after which I'm going to assign the value of the count statement to the output port. All right, so let me just end off this here, and I can start typing my sequential code inside of here. Now, the n-bit counter is, as always, a sequential circuit, which means that we require a process block. Okay, so what I'd like to do here now is create this process block, and I think it's pretty obvious that the sensitivity list of the process will contain my clock and reset signals, because these are the two signals which can cause this process to be triggered. All right, now between the begin and end process keywords, let's try and figure out what we're doing with the clock and reset here now. Well, I think for sure I'd want an asynchronous reset for this counter. And if we recall from the D flip-flop example we did last, I can write an asynchronous reset using an if statement such that I check my reset signal first, after which I check my clock statement in some else if block. All right, so I'll just place the else if statement there. And from this, we can see that it is an asynchronous. So I'm going to add these to the comments here. Asynchronous active high reset. How do I know it's active high? Because I'm checking to see when the reset is equal to 1. Then I'm going to assign the signal a value of a 4-bit 0 value. Okay. Notice that I'm assigning the value to the signal directly and not to the output port directly. All right, and we'll see the reason for that in a little bit. So my else if statement now is going to be checking my clock signal, and this should not be nothing new to us because we covered this just now in the full D flip-flop. Okay, so I'm checking rising edges here, and of course, just to be safe, I'm going to place my end if statement there. And now what I would like to do is, on each rising edge of the clock, I would like to simply, well, I know for sure I'd need to increment the clock, but what I do want to do is check to see if I am at the limit of my clock. In other words, if I've reached the maximum count, then I need to reset the counter variable to 0 because I have that wraparound counter feature. In other words, I'll go from 13, 14, 15 back down to 0, 1, 2. So I'm going to add a nested if statement here that states if count is equal to 15 in binary, or 4 ones, then I'm going to add this nested end if statement here. Then I am going to let count wrap around back to 0. And I want you to notice one thing here, that when I'm dealing with these standard logic vector 4-bit values, I place these values in double quotations as opposed to my single bit values where I placed them in single quotations. All right? Actually, so the script here has that I'm just adding count on every rising clock edge, and essentially what's going to happen is when I reach 1111 and I add 1 to that, it's going to result in a 5-bit value for 10000. In other words, the binary representation of 16. So it's going to have a carry bit coming out of that, and the 4 bits that remain inside of the count 4-bit variable will still be 0000. All right, so that means that this nested if statement isn't even that necessary. So to make life easy, I'm going to take this out here, and we'll see why it can or not necessarily is required there. Okay, so let me just add count equal count plus 1 here first. And that takes care of the counter there for me. The process that takes care of the counting. Now, how do I assign this count value to the output here? Well, I can do this outside of the process, and the reason I want to do this outside of the process is any statement outside of the process will be a concurrent statement, and it will be occurring concurrently or in parallel with the process, which means that I don't need to wait until I execute all of these lines line by line for me to assign the value of count to the output. In other words, as soon as the signal count changes inside of here, it's going to be assigned to the output port like this. All right, and that makes for a more efficient, timely implementation. All right, so I can save this. I'm going to compile it to ensure that I have no errors here. And seems as though we don't have any errors, so it's just synthesizing the design. So what I can do now is I can easily write a test bench for this circuit design here. All right, now the test bench in this case would involve me simply having a clock process, because the clocking of the device is going to take care of the counting internally. And I can have a separate process for the reset, just to test that the reset functionality works as expected. So to write a test bench for this file, I'm going to add a new VHDL file to my progress. And I'm going to just add these libraries that I need up here. Okay. Actually, I don't even need the unsigned and the arithmetic libraries, because the test bench is not going to be taking care of any arithmetic for me. I'm going to save this test bench as bin counter underscore TB. Right, and just to be safe, I'm going to name my entity the same thing. Remember, for the test bench, it's always an empty entity with your corresponding architecture. I'm going to name my architecture TB, specifying that it belongs to the particular entity. All right, just to put the basic structure of the architecture there. As before, because I'm testing this entity in the separate VHDL file, I need to define the component. And the component that I'm testing is the binary counter. All right, and I need to specify the ports and ensure that it matches the ports stated in the entity description right here. One thing we can easily do is just copy and paste these ports between the, so I'm going to remove this stuff here. I'm going to paste this stuff between the component and end component statements like this. Okay? I do not explicitly advise this for the sheer fact that you all need to get accustomed to writing these components explicitly, because if you need to write it by hand for an exam, you need the practice in doing that. Okay, and of course I'm going to create my signals for the clock, the reset, and the output. So I'm going to have clock and reset being defined as signals of type STD logic on one line, and of course I'm going to have a separate line for the output signal because this is of a different data type. It's the standard logic vector. Need to specify that it's 4 bits wide, and that takes care of my architectural declaration section. Next thing I want to do is instantiate the component that I declared above. So I'm specifying that I'm creating an instance of the binary counter component, and I'm going to do my port maps, specifying that the signal clock is being mapped to clock, the signal reset is being mapped to reset, and the output signal is being mapped to the output port. Right? Place my semicolon there. Remember, we have commas between these port map operators here. Okay, now that I've created the instance of my counter and I've taken care of defining the symbols and the component in the architectural declaration section, I can go on to write my processes. And again, the structure of this process is nothing new to us because we've been writing clock processes for the past 2 test benches. All right. Once you're writing a clock process, it's the same thing. So you don't need to worry about the structure of this. As long as you learn the structure for a clock process, it remains the same throughout for any test bench that you're writing. The only thing that may change is if you want to change the period of the clock. All right. Sorry about this. This should be less than 0 for the assignment operator. All right. Just pay attention to that. Going to wait for 20 nanoseconds. All right. So I have a uniform clock process there now, and I can just create a quick reset process here. All right, I'm going to specify that my reset signal is going to be assigned a value of 1. I'm going to wait for, say, 10 nanoseconds. And I'm going to set it back to 0 and then wait forever, which is just a simple wait statement. All right. I'm going to put my end process line here. And I believe that will take care of the test bench for this file. For the binary counter. Now I'm going to compile the design, and remember, it's a new test bench file, so I need to go over all the steps of adding the test bench file to the test bench settings window, setting the binary counter as my top level entity, etc. I'm just doing the compile process now to ensure that I don't have any syntax errors here. And well, because the process bar is in progress, that means the progress bar is in progress, that means that I'm fine there. So you see that compilation was successful. Remember to specify that a test bench belongs to an entity, or rather to the project. The first thing I need to do is select assignments from the menu bar, select settings, ensure that the simulation option is selected from the left hand side of the window. I'm going to click on the test benches button. I'm going to add a new test bench file, and this one will be my bin counter TB test bench. I'm going to browse for the file in the directory. I want to make sure that I select the bin counter underscore TB VHDL file. Once the file has been specified here, I'm going to click add to add it to the project, click OK, and we see that the binary counter test bench file now exists in the test bench settings window. Okay. Once I click OK here, the test bench is now going to exist in the down drop, and from the down drop I want to make sure that I select bin counter underscore TB, click apply, click OK, and finally I'd like to select the binary counter and make that the top level design entity of this project. Okay, once that is taken care of, I'm gonna recompile the design, and then we should be okay to simulate. Now, remember, the simulation may occur automatically depending on if the compilation was okay with ModelSim, and if not, we'd have to manually recompile the files in the ModelSim environment. Okay, I honestly can't say why it generates the waveforms automatically sometimes and why sometimes it doesn't. but at least we know the workaround if it does not. Okay, so I'm going to click on my RTL simulation button to open the model sim environment. Remember, that's this little play button to the right of the clock on the taskbar up here. All right, so let's look at what model sim says now. All right, so it seems as though my waveform was generated automatically because I'm seeing the signals existing in this area here. So let me just click zoom all. I see my test benches there being generated. All right, so if I were to zoom into this here a little bit and then scroll all the way to the left, let's look at what happens here now. Now the test bench will, the test bench will show that the counter counts on every rising edge of the clock. Notice that when my reset is high, my output on the binary counter is equal to 0. Then on every rising edge, we see my 4-bit value incrementing by 1. To see this a little more clearly, we need to be able to understand how we counted binary. So we go from 0 to 1. Then on the next rising clock edge, I go to 2, which is 0, 0, 1, 0. Then I go on to 3, 4, 5, 6. And another thing we want to check is to ensure that the wraparound from 1, 1, 1, 1 to 0, 0, 0, 0 works properly. So I'm going to slowly scroll a little bit to the right here now. And look, 1, 0, 1, 0, 1, 0, 1, 1. I'm going to go all the way until I hit 1, 1, 1, 1, and you see that I scroll back down to 0 there. Alright, so that implies that the counter works as expected, and we've just created a 4-bit binary counter. You can create binary counters of any number of bits wide, and your count will go from 0 to 2 to the power n minus 1. So I'm going to close off model sim now. Right? If your waveform did not generate automatically, feel free to pause and rewind to the section of the video where I was manually recompiling and generating the waveform in model sim. Alright, that's what I was doing for the D flip-flop. Okay, so I can close this test bench now, and just to revisit this binary counter file a little bit, if I wanted to make a 3-bit binary counter, in other words, one which counts from 0 to 7, then I would just change the size of my output and count signal to 3 bits wide, or 2 bits down to 0, and I will initialize count as 0, 0, 0, and those are the only changes I need to make. So this is a good structure for you to note when creating counters. Okay, it's a general structure that you can use throughout your design. Just going to quickly change this back to a 4-bit binary counter. Save my changes there, and we can move on to the next topic, which under the field of counters, we are going to look now at modulo n counters. All right, all of the details of the counter that I may have skipped would be stated in the lab script here on page 13, pages 12 and 13. Okay, all right, so let's go on to the modulo n counter now. Now, a modulo n counter is very similar to a binary counter, except we can specify the number of states through which the counter counts. So if I want to make a mod 5 counter, for example, the states that I will be going through are 5 possible states from 0 to 4. So I'll count from 0, 1, 2, 3, 4, and then back down to 0 for a total of 5 possible states. Sorry. By that logic, the 4-bit binary counter is a mod 16 counter because I was counting through 16 possible states. So a modulo n counter essentially allows me to place some limit on the maximum count, after which I will reset that count to 0. So let's now add a new VHDL file to our project, and we are going to write code for a modulo n counter. Okay, so the libraries that I'm using for the modulo n counter are the same as I used for the binary counter, because again, I need to do that unsigned arithmetic with some standard logic vector. All right, I'm going to create the entity, and I'm going to name this the mod, let's just say it's a mod 10 counter, which means I'm going to be counting through 10 possible states. All right, 0 through 9. A mod 10 counter And the ports of the counter are going to be the same as that for the binary counter, because remember, at the end of the day, the external ports of a counter are just the clock which drives the internal workings of the counter, the reset signal, and some output signal which provides the current count value. All right, so I'm going to have my clock and my reset as inputs of type standard underscore logic, and then I am going to have my output of type standard underscore logic underscore vector, and it's a mod 10 counter, which means I'm going to count from 0 to 9, and 9 in binary is represented as 1001, which means that I need 4 bits in that counter there. Okay, so it's going to be a 4-bit counter, very similar to what we had before. And seeing as the input-output ports of the counter are the same as the binary counter, that means that I could actually probably use the same test bench as before. All right. The architecture for this is pretty similar to that of the binary counter, in that I'm going to have this signal here of type std underscore logic underscore vector 3 down to 0. All right, and I am going to start writing the code for this architecture here. Now, again, the first thing I'm going to have is my process block, okay, and the counter is going to be sensitive to its input signals there. I'm going to place my end and begin keywords, and then I'm going to start typing the code. Again, typically with any counter, I would like to have an asynchronous reset. Okay, so I'm just going to say if reset is equal to 1, then my count is going to be equal to 0. Pretty straightforward. And I'm going to have an else statement such that if the reset signal is not 1, then I'm going to check the value of the rising edge of the clock. Okay. All right. Again, of course, if you wish, you can use the rising underscore edge function inside of these brackets here. That's just a matter of personal preference. Okay. I'm going to place my end if statement just to be safe. And inside here now, I'm going to have this nested if statement that checks to see if I am at the maximum limit. Because if I don't have some if statement to check to see if I'm at the maximum limit that I want to count to, the counter is just going to count to its maximum binary value of 15. If, however, I'm making a mod 10 counter, then my max count value is going to be equal to 1. So I'm going to have this nested if statement here that's going to check if count is equal to 9, which is the 10th state, then I'm going to reset the value of count. And this is kind of like what I was talking about earlier in the binary counter video. In the binary counter section of the video, if I were to have a nested if statement here to reset the count manually, it would look something like this, except I'll have the maximum value there. But as we saw from the test bench, the counter resets itself because it just goes to 1000 and has a carry bit value somewhere going on. All right. Now I'm checking to see if the count is equal to 9, or if I am at if counter. I'm just going to write some comments here. If counter reaches max value, reset. All right. And then I'm going to say else. In other words, if count is not equal to 9, then count is going to increment as usual. All right, I'm going to place an end if statement for this nested if statement, and that should take care of that. Let's compile this and see if we have any errors inside of here. Now, actually, I didn't save the file, so I'm going to save this as my mod 10 counter. Let me just change this to match the entity name. And it seems as if we're okay. All right. As I stated just now, I can use the same test bench file for this. The only thing I do need to change is to set the mod 10 counter as the maximum value, as the top level entity, sorry. So let me quickly do this, set as top level entity, recompile my design, and I'm going to leave the test bench settings as they were for the binary counter because the test bench would be set up for the same test bench that we're using. The only thing is I think we may have to manually recompile the VHDL test files in model sim, but I can't predict that yet, so let's see what's going to happen here now. All right, to verify the top level entity, you can just look in the hierarchy tab of the project navigator and you'd see the top level entity stated there. Okay, now it seems as if the signals were generated automatically for me. Okay, so what I'm going to do is I'm just going to pause the simulation by clicking on the stop button. I'm going to zoom in a little bit and let's see what's going on here. Okay, now which file am I simulating here? I'm simulating the mod10 counter with the binary counter underscore TB. Yeah, that's right. Okay, I'm not getting any output here, and let us see why that may be. Okay, I am just making sure that everything is fine here. The reason why I'm not getting this is that in the test bench file I forgot to set the component as the mod10 counter. Okay, so you see, simple little mistakes like that can make a big difference. All right, okay, that means that I can now recompile this. And the reason why I was allowed to just change this to mod10 counter is because the mod10 counter has the same port listing as the binary counter in the same order of clock, reset, and output. Okay, so please note that the order in which the signals are listed in the port keywords are very important. Okay, so the compilation was successful. I'm going to open the model sim software now, and let's just verify that my counter counts through 10 states and resets at 9. Okay, so I'm going to stop the simulation. I'm going to zoom all. Okay, seems as if there's still something wrong here. So let's go back to the file and let's double check some stuff here now. Mod10 counter is set as my top level entity. The binary counter underscore TB file is instantiating the mod10 counter component. Mod10 counter is spelled with a capital C. Yeah, let me just copy and paste this from the entity block of the design file and paste it in this field here just to make sure that it's correct. Yeah, all right, my signals are of type std underscore logic and my symbols have the same name, clock, reset, and output. Let's just verify that. Okay, and the signals, yes, I did forget to do something, and that is actually not a problem with the test bench. In the mod10 counter value, I forgot to assign the count signal to the output of this circuit. Okay, so again, you see that we can always end up with minor little problems there. So fingers crossed, I believe that this should be the final time we're troubleshooting and debugging this code now, and I think everything would be fine here now. Okay, so remember, this line exists outside of the process so that every time the value of count changes here, I don't need to wait until I hit all of these lines here before the end process statement before I can assign that value to the output there. Okay, so as soon as count changes within the process, it is assigned to the output port instantaneously. Okay, so running the simulator now, that should take care of everything there. the waveforms again being generated automatically for us, and we see that we have some count values now. Okay, great. So let's just zoom in and make sure everything is okay here. And we see that when we count from, we can count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and from 9 back down to 0. So you see that we just created and tested this mod 10 counter. All right, and before you even verify the operation of circuit description on the FPGA board, it's always good programming practice and good VHDL design practice to write a test bench before you mess up anything on the FPGA board, and just to ensure that your design works correctly. All right, so that takes care of modulo counters. And the BCD counter, well, I guess we just covered the BCD counter because a binary coded decimal number scheme accounts for encoding each decimal number as a 4-bit binary number, that's 0 to 9. And as stated in the lab script here, our BCD counter is essentially a mod 10 counter. All right, so that takes care of the stuff today for lab 2. I'm not gonna go into the frequency divider stuff just yet because I'll leave that for another lab session. And I think that we have had a lot of information here to absorb. And before teaching the theory of frequency dividers, we don't want to get too saturated now. Okay, so thank you for taking your time to watch this video. Again, I do apologize for not being able to make it to class today, but please note that you you um you can do this at home on your own time, on your own pace, but I will not be doing this in the lab again because this video is meant to replace the in-class lab sessions. All right, and I actually think it's a little more useful because you can all follow along at your own pace in the lab. Okay, feel free to screenshot and snip me any errors. If you are sending me images of errors, remember you can use your snipping tool in Windows, and you're going to send me the errors in this area here. And also please send me your code, because more than likely your errors will originate in your code, and I'd need to see the code before I can troubleshoot what your error is. Okay, so thanks everyone for watching, and that's it for today. Bye.